Alrighty, in this video here, we're going to talk about lesson 5.5, which is rational functions and rational inequalities. All right, so quite a bit of notes before we get into the different homework examples that you'll see. A couple of things to kind of point out. A rational function is basically a function that can be written as a fraction, in a sense. And that fraction is basically two functions on top of each other. These do not have to be polynomial functions. They can be any type of function that we know of. However, there is one thing that can't happen, and that is where the bottom function cannot equal zero, because we know when dividing by zero, it is undefined. So a rational function is just basically two functions that kind of look like a fraction, but they're one on top of the other. And the bottom function cannot equal zero. So when we're looking at the domain of these type of functions, it'll typically be whatever consists of the q of x and then exclude things that make it zero. So the domain will result in the domain of q of x except the x values in which q of x would equal zero. So if it's a square root function, you already know x can't be, or the inside function can't be a negative, and then it can't be zero either. If it's just a regular polynomial function, which is all real numbers, it'd be all those numbers except what makes those functions zero. What's a different type we get? It's the only two I can really think of top of my head, but that's basically the restriction that you would have there. All right, now in these restrictions, in which what happens when q of x does equal zero, it actually gives us part of a graph so we can kind of have an idea of what's going on. And these are called vertical asymptotes. All right, and it's where x equals c such that q of c equals zero. All right. You can have what we also call holes, and we'll get more in detail on those. But those holes are things that where we're factoring and canceling, we can see that's just a hole and not an asymptote. But we'll get further into detail. But basically, a vertical asymptote is where x equals c, where such that q of c equals zero. And to get a little bit more specific, it's where the function approaches but does not cross. Basically a vertical line. So we'll graph like a dotted vertical line, make it kind of imaginary, and then that'll be the line in which you cannot cross. We also have the same concept with horizontal asymptotes. This is basically, it's where y equals c such that, shoot, what would that be? So q of c equals zero. In this case, such that Q of X is equal to C. It's kind of the same concept there, but basically it's where it's like an imaginary horizontal line where the function can't cross. So I guess this is where the Y approaches but does not cross, and this is the same concept where the Y approaches but does not cross a horizontal line. All right, now in this situation, there are certain situations where it will cross in one part of it, but then not able to cross in a different. And we'll look at those type throughout the chapter here. If there is no horizontal asymptote, that means that there is what we call an oblique asymptote. You might see a textbook also use the word slants. But basically, it is where so again, this is if there is no horizontal asymptote, then we have a non-horizontal asymptote. Now, I have seen most of the asymptotes that y'all will deal with in this class are just linear lines or linear asymptotes, where it's like an imaginary linear line where it won't cross. I've seen them as quadratics and all kinds of other different functions as well. I don't think in this course you will go into that much detail, but if we do, I'll definitely highlight those moments. All right. After that, we do have some asymptote notation. This is something that's big in Calculus 1. When you are looking to see at what point a function is approaching at some certain x value, I can actually look at either the left or the right side of that value. And I'll give you an idea. Here's a graph. Let's say I have a vertical asymptote right here, and I have a graph that does this, and a graph that does this. I can actually have two different notations if I'm looking at a value. If I want to know what is f of x doing when x approaches c from the left side. So when you see this icon here, this is the left side of c. And if you see something like this where it's c from the right side, that's a little plus sign, this would be the right side of c. So in this situation, on the left side, I can see on the left side of this asymptote, f of x is approaching infinity. But on the right side, I can see f of x is approaching negative infinity. Ooh. And then you have just regular approaching that value. That means the left side, or that, sorry, do better notation here. That means that the value that x is approaching from the left equals the value as x approaches from the right. Whatever that value is, f of x will be at that value. Now, if they don't, which in this case they don't, then f of x would be, so if do not equal, then we say it does not exist. There is not a value at c that the f of x is approaching since it's going in two different directions. All right, so that's just some notation that you might see throughout the book, but this is a big Calculus 1 topic. If you ever take Calculus 1 next, you want to highlight this moment. Let's see. To solve for vertical asymptotes, all you have to do is set the denominator, which in this case is q of x, equal to 0. You set it, and you solve it. The next thing, there's like a three-step process here, but to solve for horizontal asymptotes, we have three rules. If f of x, let's rewrite this one. If f of x is written as p of x over q of x, then let's say this can also be written as ax to the n, and then this can be written as ax to the m. And this can be a continuous function there. We don't know what it is, but let's just say this. And I know that looks like a double N there, so let's make sure we know that this is a M. So basically, when we're looking at the highest or the leading coefficient of both of these polynomials to determine if there's a horizontal asymptote, if N is less than M, then the answer is, I'm going to abbreviate here, so horizontal asymptote will just be y equals 0, straight up. So if this number is less than this number, or you can read it as this number is greater than this number, the answer is automatically y equals 0, no other math needed. If n is equal to m, then the horizontal asymptote will be equal to the leading coefficient. So let's actually make this a different coefficient. Let's call it b. So then this will just be y equals a over b. So if n equals m, then we'll just divide the leading coefficient. If n is greater than m, there is no horizontal asymptote. But if there's no horizontal asymptote, then we find a oblique asymptote. So just abbreviating here, oblique asymptote using either long or synthetic division. Right, so if there's no horizontal asymptote, we have to look for oblique. If there is a horizontal, then there will not be an oblique. No need to do all the extra work. All right, now after we are able to determine every aspect of these rational functions, you need to be able to graph them. So I think your textbook has like 17 steps to graph. I have 4. All right, so to graph, you want to start off by simply factoring the denominator and numerator. I think I just butchered that numerator. Let's try that again. All right, once you factored the numerator and the denominator, this will help us know if factors are cancelable, then it has a hole, which basically just looks like this. It just has a hole in the graph. If it's cancelable, if not, it is, or if it is not, then the remaining factors of the denominator are your vertical asymptotes. Then determine horizontal asymptotes or oblique asymptotes by doing the steps. So either we determine there is or we determine there's not, and I have to go find an oblique. Then you want to find any x and y intercepts to help you graph, and then plot points until you see what the graph is doing. Most graphs, just to give you an idea, have branches on these guys. This is just an example. So basically, when you can determine your asymptotes and kind of see that a point's here or there or there or there, you can kind of see, all right, that's where a branch is going to be located, and then kind of sketch it from there. So I'll show you some examples of that as well. All right, the last thing you're going to have to be able to do on this is solve rational inequalities. And to do this, the biggest issue is you have to set the inequality to 0. Either side, just get all the rational functions on one side, make it 0. And by doing that, you must add or subtract the rational terms to become one rational term. This will then allow you to be able to find boundary points. Then we can test. Then we can find, well, we can use test points to determine if the intervals are true or false. Just like we did with polynomial inequalities, rational inequalities have the same concept. It's just a little bit more work than polynomials. All right, so that's pretty much everything that's in 5.5. So let's do some examples so that we understand what I just said and understand your homework. I'm going to first look at number 3 here. Now, if we look at what the textbook is asking us to do, there's not much it's asking us to do here, but I'm going to do a lot of asking just so that on the homework you have it to where like the homework will ask, what's just the vertical asymptote? What's the horizontal asymptote? Graph these functions. Just find the vertical and horizontal asymptote, and ask questions, but like one singular question. So what I'm going to do is I'm not going to do as many questions as usual. I'm just going to take a question and then just ask all the questions for it. All right, so here we go. So functions that you'll see are things that look like this. So f of x equals x squared minus 4 over x plus 2. Remember, step 1 is to factor. Hopefully you see this is a difference of squares, and we'll factor into x minus 2, x plus 2 over x plus 2. So when I'm looking at this, I can see that x plus 2 and x plus 2 will cancel. So therefore, I have a whole at x plus 2 equals 0, which that means I have a whole at x equals negative 2. If they ask you for a specific value, then you just take negative 2 and you plug it into the remaining function. So in this case, this would be negative 2 minus 2, which equals negative 4. So your coordinate here would be negative 2, negative 4. I don't remember if it asked for a coordinate. I don't think it did, but I do know in some examples in other textbooks, they ask for the coordinate of the whole, and this is how you would calculate. So we factored, canceled. Things that canceled became a whole. Anything left in the denominator would be a vertical asymptote. So here, there are no vertical asymptotes. So we factored, canceled. Things that got canceled became a whole. Anything remaining would have been a vertical asymptote, but in this case, there is no vertical asymptote. Fourth thing, is there a horizontal asymptote? So if the denominator is larger than the numerator, then there is no horizontal asymptote. Right? Had the denominator been larger than the numerator, then it would automatically been zero. And if they would have been the same, then we would had to just divide their coefficients. So therefore, to find the oblique asymptote, you can do either synthetic division or long division. Remember, with synthetic division, you can use it as long as it's divided by x minus c. So this is the term it is. So it's x plus or minus some number. So I'm going to use the 0, which is -2, and then use the coefficient. So that's going to be 1 for x squared, 0 for x, and -4 for my constant. Don't forget you have to have a coefficient for each term. So that's -2, that's -2, that's 4, that's 0. All right, so in this case, x minus 2, oh man, hold on. To recall this event, no, there's another example. That's right. Okay. Got over anxious here. Since this value was able to get canceled, that tells me that there will not be an oblique asymptote because it got canceled. Had it been a vertical asymptote, then I could. So we did all this work for nothing. But it's a good learning thing. So there's no horizontal asymptote, but because it got canceled as a whole, there is no oblique either. All right. And that only happens when you end up with nothing as the denominator after canceling. So there's no horizontal asymptote or no oblique asymptote. So far, we could do this. So we have a whole at -2, -4, and this value at a whole. And then you basically graph x minus 2. So x minus 2 is a linear point that has a y-intercept at -2. And then because we know it's linear, you can kind of sketch the rest of your graph. If you need more points, you can find more points to help you out, like the x and y-intercept. Now, in this case, I did find the y-intercept, but that's because I know when a function is in this form, this is the y-intercept, and that's what I was able to plot. And then once I knew it was a linear line, 2 points make a line, so I was able to sketch the rest. If you need more points to kind of see that, then you just keep kind of going through that process. All right, so in that situation, that no oblique when it's a whole, not a vertical asymptote left. All right, so number 8. So this says f of x equals x plus 2 over x squared minus 9. So while working through this, I go through all my steps. I'm going to factor. So that's going to be x plus 2. Hopefully you see that's a difference of squares. So that's x minus 3 x plus 3. I cannot cancel, so no holes. And because I can't cancel, I have vertical asymptotes at x minus 3 equals 0 and x plus 3 equals 0. So that means x equals 3 and x equals negative 3 are my vertical asymptotes. Horizontal asymptotes, the denominator is greater than the numerator in the degree department, so that means y equals 0. And because I do have a horizontal, there are no oblique asymptotes. So I can kind of sketch the graph here. So I see I got one at negative 3. Here is what a vertical asymptote roughly looks like. You have a nice computer program that does this for you. There is your x equals 3 and x equals negative 3, and then you technically have one at y equals 0. So we have a function that looks like this. Now, to help you figure out where things are at, I just like to get some test points. I'll just choose a value that's to the left of negative 3. So I'm going to try to figure out what is f of negative 4. Once I determine it's either positive or negative, then I know that I have a branch that looks like this. So here we go. So negative 4 plus 2 is a negative. Negative 4 squared is positive. 16 minus 9 is a positive. So that tells me that I get a negative. Since I got, and again, I don't care about the number. I just care about the sign itself because that will tell me pretty much what I'm graphing. So a negative here, I know I'm going to be below the x-axis. Same concept here. Choose a value of between negative 3 and 3. Hmm. These can get tricky here. All right, so when working through this, I'm going to choose a number between 3 and negative 3. I'm going to choose 0. And when I do that, I get a positive 2 and a negative 9. So I know I get a negative number. So 0 here tells me I'm going to be below the 0. So that gives me a coordinate here. Now, typically, that means that I would have a quadratic here in most typical situations. This one is one of those trickier ones. So for me to assume that it does this quadratic, I have a value here. So I'm thinking it's going to be a quadratic here. But to make sure it's not a cubic or any other weird function, I'm just going to choose a number close to negative 3. So I'm just going to choose f of negative 2. Again, I'm just looking for the signs. Hopefully it stays negative, and I know I'm good to go on that side. So that actually gives me 0. And then that's negative 2 squared, 4 is negative, but regardless, I get 0. That tells me at negative 2, I get 0. That means in this section of my graphing, it does cross this horizontal asymptote, which it can. And if that's possible, that means I'm not going to have a quadratic. I'm going to have a function that does this. It's not going to bounce back through. It's only going to go once. The only issue is I don't know if it's going to come this direction. So what I'm going to do is I'm going to plug something close to 3. In this case, that's going to be 4 over negative, which gives me a negative. So that means here I'm somewhere in the negative, so I'm not going to cross again. So then I would have a result that does something like this. So this is one of those situations you definitely got to try a little bit more test points to kind of see what's going on there. So watch out for that. The other part's pretty nice on the branches. I can just choose a number to the left of 3, and let's just choose positive 4. So I get a positive over a positive. So that gives me a positive result. So that means I have the situation. Branches that will go across will typically be done inside the middle of 2 different vertical asymptotes. Doesn't always happen, but just try and test numbers to kind of see where they land is the best route to see if it does in fact do it. Next one is, let's look at number 10. F of x equals 2x squared plus 2x minus 4. And we get x squared plus 2x plus 1. All right, so again, first step, I'm going to factor this. Hopefully you see that they all have a 2 in common. So this is a 2 and then an x squared plus x minus 2. And then this is x squared plus 2x plus 1. So I'll factor it now. I could have done that on the bottom, but I wanted to make sure I do it all together for you. So two numbers that multiply -2 but add up to 1 will be x plus 2, x minus 1. Two numbers that multiply 1 and add to 2 would be x plus 1, x plus 1. Again, that gives me 1, adds up to 2. This multiplies -2, gives me 1. So there's my factors. So in my second thing, I cannot cancel anything because those are both positive. So that means no wholes. I do have some vertical asymptotes. They just happen to be the same value, so I'll need to solve it one time. So I got a vertical asymptote at -1. Horizontal asymptotes, they are the same value, so 2 and 2. So that means my answer will be the leading coefficient. So that's going to be 2 over an imaginary 1, which in this case is just 2. That means that there are no oblique asymptotes. So now I'm ready to sketch my graph. So again, I'm going to start with some things I know. So here's -1. Here's my horizontal asymptote. So again, I'm going to choose numbers left and right to see if it's greater than or less than 2. So here we go. I'm going to choose f of -2. It doesn't matter which one you use, whatever's fastest for you. I think these are the fastest way to do answers. So that's going to be 2, 0, and then was that -3? And then this would be -1, -1. Regardless, I get the answer of 0. So that means I crossed the horizontal asymptote again. So when that happens, sheesh, doesn't happen very often, but for these examples, they're happening every time. So that means I need to determine, how's it go? Does it go like this or does it go like this? All right, to do that, I should probably choose another value. So I'll choose f of -3. This will kind of help me determine if I graph here, then I have a function that's going to do this. If I graph here, then I have a function that's going to do this. All right, so when we're plugging them in, let's kind of work it out. So f of -3, this time I'm going to plug it in this one. So this gives me -1. This gives me -4. This will give me -2, -2. So that will give me +4. So it gives me +8, +4. So it gives me a +2. Man, I got thrown off there. Hold on. That's not the 0 line. This is the 0 line. All right, so I got my point. I want to assume it does this, but then I checked this point and I got this point here. This crosses the line, but since I'm over here, I can then determine that my branch does something like this. All right, kind of real quickly, there's a mathematical way to determine these. So I want to kind of bounce back to the other question to show you this as well. Once you determine your horizontal asymptote here, all you want to do is take your equation, set it equal to that horizontal asymptote. This, of course, will zero out. So then you get x plus 2 equals 0. So then that tells you that it actually crosses at -2, which it did. And if you get that value, we need to see something like this. So instead of us guessing some numbers and potentially not getting it right, we can go around this process and then choose numbers left and right to see, all right, is it going up or down? Bouncing back over here, I can do the same concept. I didn't think about it until here just now. But I can take I'm just taking the factored version. You can actually take any version you want. Set it equal to 2. Um, Actually, it might actually be easier. Hold on. To use that first one. Even though, I don't know, you go back and forth on what is quickest. Gotta do all the math regardless. All right, so I'm gonna set equals 0. When I do that, I'm gonna cross multiply and divide. So becomes 2x squared plus 2x minus 4. Again, I'll take this, multiply it to the 2. Then I get 2x squared plus 4x plus 2. Set it equal to 0. So when I subtract 2x squared, they cancel. Subtract 4x. Subtract 2. That gives me negative 2x minus 6. Now, originally I did that thinking I was going to solve a quadratic. So now I'll add 6. And then I'll divide by negative 2. And so I get negative 3. So here's negative 3, and it tells me it's going to equal at 2. And then what I'll need to do after that is choose some test points. We happen to choose this one, so I could see it does this. And that means then it'll plateau on that horizontal asymptote as well. It won't shoot up. And then we can kind of play with the other side. And since I don't see another value in which it's only got one value here, then I just need to choose a value to see if it's going to be on the top or bottom. So I'm just going to choose f of 0. And again, you can plug it into either one of them. So I get a positive, positive, negative when you plug in a 0 into these. So positive, positive, negative, and then positive, positive. Oop, put an extra parentheses there. So that tells me that's going to be a negative over a positive, which is a negative. So if I get a negative, I want to be over here. So that tells me I'm going to have a function that does something like this. If your homework asks you for specific points, go look for the specific values so that you can find the correct corresponding point to put it, and then you should be able to build a branch around that. So in this case, I would say that's 2 times 2, which is 4, negative 4. So this would be negative 4 over 1 plus 1, which is a 2. So you get negative 2. So at 0, I should have a negative 2. So I should actually be closer here, kind of doing something like that or something like that. Just in case it needs specific points. I know some homeworks ask for certain values, some just say click a spot where the branch will go and it'll do the graphing for you. Alrighty, let's see. That was number 10. So let's look at number 19. Yeah, I'm just trying to grab some examples that look pretty similar to your homework. And we're just going to do all the work that's required, even though the homework might just ask for one question. All right, so first thing we want to factor, nothing to factor, nothing to cancel, so that means no holes. Vertical asymptotes then would just be x minus 1 equals 0, so that's x equals 1. Horizontal asymptotes, the denominator has a degree of 1, and the numerator does not have a degree at all, so that means the denominator is greater, so that means it's y equals 0, which then tells me there are no oblique asymptotes. So let's sketch this graph. Again, check it. So do 5 over x minus 1 equals 0. When I do that, I get 5 equals 0. So that means it does not cross our horizontal asymptote, which is typically the ones you get. But we have gotten quite a bit of ones that it does. There we go. So there's your vertical asymptote. Here is your horizontal asymptote. There are no oblique and there are no intercepts of the horizontal asymptote. So now all I got to do is just plug in values. So I want to plug in 0. And I get a positive over a negative, which gives me a negative. To give you maybe a specific value here, this is going to be 5 over negative 1, which is negative 5. So 1, 2, 3, 4, 5. Here's my negative, so therefore I know my graph is going to do this because it does not cross that horizontal asymptote. I'll try f of x equals 2. So it's going to be 5 over 2 minus 1, which is 5 over 1, which is just 5. 1, 2, 3, 4, 5. So then for I know it does something like this. Again, not able to cross the x-intercept or the y-intercept. It definitely does not cross vertical asymptotes. I did not mean to say intercepts. But horizontal and oblique asymptotes, it definitely can, depending on your situation. Let's look at number 20. F of x equals x squared plus 3 over x plus 3. In this example here, I cannot factor anything. I cannot cancel anything, so therefore there are no holes. Vertical asymptote would just be x plus 3 equals 0, so that's x equals negative 3. Uh, there are no horizontal asymptotes because the denominator is less than the numerator. So to find my oblique asymptotes, I'm going to use synthetic division. Again, nothing canceled, so I know I can do this. So that's going to be a 1 for my x squared, 0 for my x, 3 for my constant. What was that, 9? 12. All right, when dealing with the oblique asymptote, I could care less about the remainder. My oblique asymptote will be the actual coefficient. So this is 1x minus 3. So that is my oblique asymptote. So when I come over here to graph it, 1, 2, 3, and then it goes up 1 over 1. So I'm going to put these open circles for right now. And that tells me I have an oblique asymptote that roughly looks like this. Two lines make a two dots make a line. But those are open circles because it's an oblique line. It's not part of the function, so it's where it can't cross. You do technically need to take this and set it equal. When we do that, when I take this and I multiply to this, I actually get this. So this is a difference of squares, so this would be x squared minus 9. And then I'll subtract x squared, and I get 3 equals negative 9, which is not true. So that means it does not cross this oblique asymptote at all. So in the situation, there's usually just one branch. You just got to figure out how does it look. Best way to do this is to kind of graph it with some random points to see what it does. We do have a vertical asymptote though. So here's my sections. I could have a branch here. I could have a branch here. I could have a branch here, and I could have a branch here. And then none of them crossed. So all I gotta do is just kind of figure out where does these fall. I like to start with the vertical asymptote to see if it's gonna fall here or here or here or here. And this will kind of determine what these values are. So I need the specific points because I'm not just dealing with a positive negative situation. So here we go. So we're gonna try f of negative 4. So that gives me 16 plus 3, negative 4 plus 3. That gives me 19, negative 1. That gives me negative 19. All right, so negative 19, how far will that go? All right, does negative 19 fall on this one? The best way to do that, plug in negative 4. If I plug in negative 4, that gives me negative 7. So that means negative 19 is somewhere way down here below that line. So that's going to tell me my branch here does something like this. Again, negative 7 was the threshold. I hit negative 19, so it's up below it. Had I had, like I said, plug negative 4 here, got negative 7. Had it been less than that, then I would have known I had something up here. All right, now I'm going to choose something to the right. I like to keep it easy, so I'm just going to choose 0. In this case, that would be 0 plus 3, 0 plus 3. 3 divided by 3 is 1. So at 0, 1, I can really see that it's right here without having to plug it in there, but I can see the threshold would have been negative 3. So therefore, I have something that looks like this. All right, and then there's your two branches. Again, I don't know how specific your homework's going to be. It might ask for a point or two, and then it'll kind of sketch the branch for you. All right, just one more of these type of questions, and then we'll talk about how to solve inequalities. So let's look at number 26. And it is f of x equals negative 3x plus 5 over x minus 2. I cannot factor anything, therefore I cannot cancel anything, so there are no holes. Vertical asymptote then would be x minus 2 equals 0, so that means it's x equals 2. Horizontal asymptote, since they are the same exponent, I just divide their coefficients. So it's going to be negative 3 divided by 1, which in this case is just negative 3, which then tells me there are no oblique asymptotes. All right, so the only other little extra thing I got to do is to set my equation equal to the horizontal asymptote. And let's see if what happens. Negative 3x plus 5. This will give me, again, I'm taking this and multiplying to this. So that gives me negative 3x plus 6. And then plus 3x plus 3x. I get 5 equals 6, which is not true. So it does not cross my horizontal asymptote. I feel like I got PTSD from the last couple examples to make sure we check it now, which is a good reminder, I guess. All right, so vertical asymptote. Is right there. My horizontal asymptote is right there. All I gotta do now is figure out where it falls on the branch because again, there are no crossings of these asymptotes. So let's try f of 0. So that's going to give me 5 over negative 2. So that's negative 0.25. Here's 0. Negative 2.5 would fall about right here. So that tells me I have a branch that looks like this. Now I'm going to choose f of 3. So that's going to give me negative 9 plus 5. 3 minus 2. That's going to give me negative 4 over 1, which is negative 4. So negative 4 does fall below, and therefore I have a branch like this. All right, one thing to watch out. It doesn't always look like this. Make sure you check it. We've seen lots of different examples. If you need more examples, let me know and I'll do some more. I know this can kind of get tricky on determining does it cross that horizontal or oblique asymptote. All right, the next big challenge I'll have on this homework is to know how to solve rational inequalities. So let's look at number 57. So it's going to be 2x less than 4 over x plus 1. Before I can start looking for boundary numbers, I have to set this inequality to 0. Either I subtract this over or subtract this over. It doesn't matter. I like to have everything on the left, but it doesn't matter. Just make sure you keep your signs correct. So this would be 2x minus 4 over x plus 1. I have to combine these rational equation or terms into 1. So this right here, I can put a whole number over 1 to make it rational. The next thing to do is to determine what do I have to multiply by to make these have the same denominator. And hopefully you're saying, well, this is a 1, I just got to multiply by x plus 1. And you will be correct. I don't have to do anything to this, but if I do it to the bottom, I have to do it to the top. So this now becomes 2x squared plus 2x over x plus 1 minus 4 over x plus 1. Once the denominators are the same, I can write it out all at once. So 2x squared plus 2x minus 4 over x plus 1. That is my gigantic inequality here. All right. Now that I have this, to find your boundary numbers, you just have to set the denominator equal to 0 and the numerator equal to 0. So let's do that. So I'm going to set x plus 1 equal to 0, and I get negative 1. That's a potential boundary number. Take 2x squared plus 2x minus 4 equal to 0. And if I divide them all by 2, I get x squared plus x minus 2 equals 0. Factor that out. I get x plus 2, x minus 1. That right there, multiply negative 2, add to 2. So I get x equals negative 2 and x equals 1. These are all possible boundary numbers. So that means I get my number line here. Here's 1. Here's negative 1. Let's space that out a little bit more. Here's negative 1. Here is negative 2. You don't have to have an even spacing. You're just putting some test numbers here. So I'm going to test out negative 3, Yes, negative 1.5, 0, and 2. And I'm trying to determine, is it going to be a negative since it's less than 0? It does not matter at which time you plug this in. I'm just going to plug it in here. So here we go. So this is going to be 2 times, oh, that would be a positive 9, 18, negative 6, be 12. 12 minus 4 is a positive. And then that's a negative, which gives me a negative. So this works. This is less than 0. Now negative 1.5. If I write that as a fraction, that's negative 3, 2. Squared negative 3, 2, and you get 9 fourths. 9 fourths times 2, 9 halves. 9 halves plus 2 times 3 over 2 is just 3. So 9 halves plus 3. Well, 9 halves is 4.5 plus 3 is 7.5, which will be a positive. And then negative plus a 1, negative 1/2 plus 1 would give me a negative. So that would give me a negative. So that works. That means negative 2 won't be a boundary number because it'll go all the way through, I think. Hold on. Actually, that might be false. Does it give us 0 in between? It does. So I'll talk about that in a second. I feel like I need to do this. Let's check this work in the calculator. Make sure I got this calculated right. All right, so again, that's negative 1.5 times negative 1.5 times 2. Ah, that's right. 2 times negative 1.5 would be negative 3, which is going to give me 1.5. Okay, okay. Should probably do this on paper versus in our head. All right, so this is negative over negative, which gives you a positive, which will not work. Had it worked, though, I would need to make sure that negative 2 doesn't give me 0 on the bottom of the denominator, because then I would have 2 sets of interval. In that situation, negative 2 wouldn't have, so I could have the whole continuous thing, but this part didn't work anyways. But a different story for a different day. All right, plug in 0. This is a lot easier. This is a negative over a positive, which gives me a negative, so that does work. Plug in a 2. 2 squared is 4. 4 times 2 is 8. 2 times 2 is 4. That would cancel out. That's a positive. And then that's a positive, which gives us a positive, which would be too big. All right, so then these are what works. So my answer would be negative infinity to negative 2. Again, there's no line on inequality, so it gets a parentheses. Union negative 1 to 1. All right, so there you go. There's an example there. But of course, let's do another one to make sure we grasp the concepts. So let's look at number 66. So we get 1 over x minus 4 is greater than or equal to 1 over x plus 1. Again, I'll move things from left to right. To work out things that aren't so easy because it has a 1, just take the denominator of this side and then take the denominator on this side. By multiplying it, these are now going to end up being the exact same thing, but what I do to one side, I have to do to the other. Or sorry, whatever I do to the bottom of the rational equation or term, I have to do it to the top. That's the correct way to say that. All right, so this will become x plus 1 over. I don't want to multiply that, so I'm going to keep it like this. All right, so when I do that, this becomes x plus 1. I'm going to go ahead and distribute this negative, so that'll give me negative x plus 4. Keep this all the same, but I only got to write it down one time because they're like terms. That will cancel. That'll give me 5 over x plus 1, x minus 4. So my only test points are going to be what's on the bottom, because obviously if I set 5 equal to 0, that won't give me anything. So here's my boundary points. So x plus 1 equals 0. That'd be x equals -1. X minus 4 equals 0. That'd be x equals 4. So those are my only boundary numbers. So let's check it. And again, you can plug it in at any moment. I just choose to do the last one. All right, so if I take -1, obviously it's going to be positive on the bottom. So that's going to be a 0. Oh, let's try to not put in our boundary numbers because they would give us 0. Let's try -2 here. We'll try 0 here and 5 here. Now, they're getting overzealous. Let's slow it down. All right, so we get a positive, negative, negative. Because that'll give me negative, that give me a negative, that gives me positive or positive, which is a positive. I do want it to be greater than or equal to 0, so that works. Plug in 0, so I get a positive, positive, negative. So that gives me a positive or a negative, which gives me a negative. Doesn't work. This is a 4, by the way. This right here, 5, so that's a positive, 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 positive or positive, which gives me a positive. So that works. So I get -infinity to -1. This time I get a bracket because it's actually included. Union bracket 4 to infinity. All right. They did throw a word problem at you, but the word problem's not too terrible. So let's look at number 69. It says April raises species of aquarium fish, and the total number of fish she has follows this formula. So P of T equals 200 T over T plus 1, where T is greater than or equal to 0 represents the number of months since she began. So if I plug in 0, that will be how many fish she had at the very beginning. So part A says sketch the graph of P of T for T greater than or equal to 0. So let's find some things. I can't factor. I can't cancel, so no holes. Two, my vertical asymptote would be T plus 1, which equals 0, so T equals -1. Horizontal asymptotes, they actually have the same denominator, so that's going to be y, or they have the same degree. So I just divide their leading coefficient. So it's 200 divided by 1, which is just 200, which means there are no oblique asymptotes. So to sketch this graph, here's -1. All right. The issue is right here. Well, let me keep going. So 200. Let's pretend, so I'm not going to write 200 dots, but this is 200. All right, so because it does give us this remark and it says T is greater than or equal to 0, I cannot graph anything less than 0. So one of the test points I need to find is, well, what is P of 0? If I plug in 0, I should get 0 over 1, which is 0. So that means I have a point right here. So that's actually where it starts. Next thing I need to do is just verify that it doesn't cross, or maybe it does. All right, when I do that, again, taking this times this, I get 200t equals 200t plus 200. So I'll subtract 200t. When I do that, that gives me 0 equals 200, which is not true. So it does not cross this horizontal asymptote. I just need to know, does it go this way or does it go this way? So I'm going to choose P of 1. And when I do that, I get 200 over, what's that, 1 plus 1, which is 2, which gives me 100. So that's going to be above the x-axis, so that's going to give me something like this. Right? Won't cross it, and then this is going to shoot up, and then somewhere. I don't know if it shoots way up. I don't know if it gradually goes, but it's going to do something like that as a sketch. Part B then says, what happens to April's fish's populations in the long run? I can see that in the long run, it looks like it's going to plateau 200. So I'm going to say it approaches 200 fish. Or you can say it plateaus. I don't quite know what the verbiage was on the homework. I think it said approaches, but it kind of plateaus right there at 200. Doesn't get to 200, but it won't go over 200. All right, so that kind of concludes 5.5. A lot of notes and a lot of different examples there. I know I went way in depth in the examples than I needed to, but I just wanted to make sure you had every type of situation you could face on the homework. And as always, if you need me to do more, let me know. Until the next video.